So my talk today is going to be, as was said, on restructuring categorical predictors using L1 penalties with the application to Stillbirth prediction. And this was the work that I completed in my honours year, which I finished mid last year. And as mentioned, I was lucky enough to receive the honours year scholarship from the Society. So I thought I'd better start off by telling you what I did with it. So I used it to travel to the international workshop on statistical modelling that was held in July last year. And I managed exactly one photograph from the entire event, a very blurry photo of me next to my poster during the presentation. And I'd like to share, I guess, some of the lessons I learned through this. Two of them being not so important and one a little bit more. First up, never pack your poster in your checked baggage because you will end up in the Portugal Officeworks equivalent trying to print your poster in very broken Portuguese. Secondly, try and bribe the people who assign the poster spots so you can be close to the food table. People are automatically forced to talk to you. And for clarification, I did not bribe anyone, I just got incredibly lucky. And finally, and most importantly, I guess I got a lot of exposure to some very cool and diverse statistical techniques through a lot of PhD research students' projects. And there was, of interest actually, a lot of presentations on dolphin movements that year. So if you enjoy that work, the conference proceedings could be a good read for you. So, what motivated the project? This was actually part of originally a larger project that evolved from one that was led by Gavin Pereira in the School of Public Health. And their project goal was to build a tool that could ultimately accurately detect stillbirths with routinely generated data. And they've actually recently just published in Nature. So the data they used comprised entirely of categorical predictors, and an interest arose quite early on in the project to develop a model that was not only accurate, but was also interpretable. Now, stillbirth, for some background, is when the fetus dies in the womb in the pregnancy. So quite a tragic event, and that has a huge impact, moving around some wires there, huge impact on both individuals, families and communities. And Australia has actually one of the highest stillbirth rates in the developed world. So my talk today, I'm going to start off with things we kind of already know, regression with categorical predictors, move on to regularization and the structured fusion penalty, which was kind of the main focus of my honours dissertation. And then finally, apply some of that work to modelling stillbirth. Now, hopefully at the end of this, you'll kind of have an idea of the motivation behind the penalty. I'll be able to highlight some key characteristics of the resultant solution. And the dream being, obviously, that this, a little bit of inspiration to maybe go out and use this penalty in your own work. There will not, unfortunately, depending on your stance, be a Bayesian interpretation of the penalty, nor a deep dive discussion into computation. Cool. So let's start at the very beginning, something we all know. Straight off the bat, just a simple linear regression model where we have some response Y with categorical predictors X. Now let's add the stipulation that we're only working with categorical predictors. So to build regression models with categorical predictors, we first have to encode each predictor using dummy encoding. So if we have a predictor with L levels, we need L-1 indicator variables, and this increases immediately the number of parameters that require estimation. So we can rewrite our model just with a little bit more specificity around our indexing, but it's essentially the same thing. The complexity, however, comes in when we go to make our interpretations, because you really have to consider the parameter estimates of each indicator variable to understand the predictor effect on the response as a whole. And if you can imagine you have 20 predictors and they each have 20 levels, that's quite a painful task in some senses. So when we go to build our model, of course, we need to pay attention to the variance of the model. So when dealing with lots of indicator variables, we're more likely to build a model off the bat that's something like what's listed in green here. A high variance model that is inclined to model the noise, when we're really trying to, of course, match as closely as possible the black line. The goal then is to get something close to blue that has low training and testing rates, but doesn't have, I guess, doesn't model the noise such as we see in the green line. So as you may guess, the obvious solution to that may be to regularize. So when we have lots of parameters that require estimation, especially and that's the case with categorical predictors, our models are either often fitted or overfitted or cannot be fitted. So one of the things we can do is regularize. So when we calculate our regularized estimates, we do so by minimizing the negative log likelihood with the addition of some penalty function of the predictors. So there's lots of different penalties out there, and your choice is a little bit dependent on what you're hoping to achieve with your solution. So here we have a main focus on the L1-Norm, penalties that use the L1-Norm, because it allows both the shrinkage and selection. So before we kind of go into the penalties, I guess I want to talk about what you might ideally like in the structure of a resultant solution when you're working with categorical predictors. So let's kind of think of it, this example where we're trying to build a predictive model of the amount of time spent in a wait emergency rating room based upon the pain rating upon arrival. So your patients arrive and they give you a rating from 1 to 10 based on the pain they're currently feeling. 10 being, they've chopped off their arm on the edge of life. 1 being that they've rocked up with a sniffle and a little bit of a bruise on their knee. And that's actually outside normal times where I can't imagine rocking up to an emergency room with a cold sniffle and a sore throat is particularly appreciated. So what if we were to go ahead and fit an unregularized model? And sorry, I'll backtrack a little bit there. What we'd expect in this circumstance is that patients with a high pain rating don't actually spend that much time in the emergency room. They push straight out onto a specialist ward, out to see a surgeon, etc. And those who kind of rock up with nothing particularly wrong with them, they're going to be made to wait quite a while. So it's got that inverse relationship there. So if we were to build a model and then plot the parameter estimates, what we would expect is a somewhat downward kind of trend in the profile. What often happens though is you might have something like the black line profile here, where you have quite sharp jumps between the estimates of your parameter estimates. So if you look at the example circled 1, between 3 and 4, you have quite a sharp raise, which you might not be expecting. Now, what you might want to do then is enforce a little bit of structure. So here, the pay rating upon arrival is an ordinal predictor. Maybe we want to account for that ordinal structure when we go about regularizing. So what we would also like to do is, say we produce regularized estimates, that's the red line here. We have that downward trend, but in the bubble circle 2, we actually have the parameter estimates to be identical. And what this allows us to do is create a grouping of these levels so that we can make interpretations about the group instead of the levels individually. And hopefully you can see that instead of them making comparisons about the 10 different levels in reference to the reference, you now have smaller subsets that you can make interpretations as a whole about. And this has quite large, I guess, positive effects when you're thinking about a 100-level predictor. So, how do we actually go about doing that? There is 2 penalties that have been developed, one for ordinal data and one for nominal data. These were first published about a decade ago by Tutz and Gertheis in some of their papers. So the penalties use L1 norms, but with slightly differing structures within the norm. So the ordinal penalty accounts for the fact that you have that organized relationship between the levels. So what we do is we penalize the consecutive pairwise differences of coefficient estimates, encouraging them to be as small as possible. So to make the difference as small as possible, what ends up happening is it shrinks to 0 and those levels merge together to form, I guess, a combined level. Now that fusion effect is something we might want to do for nominal predictors as well. So though it's not appropriate here to penalize just the consecutive pairwise differences because there's no structure between the levels, relationship between the levels. So instead what we do is we put a less specific penalty on it and we instead penalize all pairwise differences, encouraging them to be as small as possible. So it gets the similar kind of characteristics in the resultant solution. So when investigating, I'll actually move to the next slide. So I know I said I wasn't going to talk about computation, and I'm not really in depth, but I did want to show you these depictions of the feasible solution space when we consider a single predictive variable with 3 levels. first being the reference and then 2 indicator variables to encode that. So the one image that really resonated from, I guess, my first year of studies was that depiction that's shown in all texts about regularization. It's that feasible region for the LASSO penalty, shown in a very similar blue color as well. And that image has always stuck with me for some reason, probably just because of the simplicity of that. So when I was researching these penalties, I was quite surprised that I couldn't find something of similar for them. So one small task we did last year was to create them. And though it's not a particularly, obviously, strenuous task, I think it adds a little bit of comparative value because you can just compare the feasible space and it adds a little bit of value there. So we can see the varying shapes between the ordinal on the left and the nominal on the right, which occurs because of that structure within the L1-Norm. Cool. So let's return, I guess, to why we're here. The overall aim of this project was to build a good model of to predict stillbirth occurrence and hopefully make it interpretable because of the number of categorical predictors that we were dealing with. So we kind of initialize our model with our response variable S, which is the outcome of a single pregnancy. So 1 if the outcome is a stillbirth and 0 if the outcome is a live birth. We then set up our logistic regression model with the linear combination of our indicator variables. Cool. So we are going to build that logistic regression model, but we're also going to build 3 more regularized models. And as you can probably guess, one of them will be using the structured fusion penalties. The other 2 will be using penalties that are quite more widely published in literature. So the first being the LASSO penalty, which is probably one of the most widely used penalties out there. Now, when we think of categorical predictors, what the LASSO actually does is perform variable selection at the indicator level. So it ignores the fact that indicators, by the way that indicator variables are formed, belong to a larger, I guess, grouping being the predictor that they're derived from. So when you select them, no attention is paid towards this. We just pick indicator variables here and there based on significance. That doesn't make this the best option for making good interpretations from the output model, but we have included it here for the comparative sake. We've also included the group LASSO. This is more applicable to regularizing categorical predictors, just because it allows you to do that grouping of the indicator variables. So what happens when you apply the group LASSO is that instead of selecting at the indicator variable level, you say, look at the significance of the group together. They either selection either occurs at that group level, so either all indicator variables are in for that predictor or all are out. And it just allows for slightly more interpretable models. Now, the data that we're going to use was kindly provided as part of a larger study. And it's sourced from the WA Midwives Notification System, the Birth Registry, Hospital Morbidity System, Register of Developmental Anomalies, and the Family Connections database. So an incredibly rich source. It includes all singleton births in Western Australia from the beginning of 1980 all the way up to the end of 2015. So after we did some cleaning and quality checks, we're left with about 750,000 records, of which just over 5,000 were stillbirths. So a relatively low prevalence rate in the general population. But obviously, each one of them has a huge impact on the family or individual that happened to. So from there, we downsampled to create a training set which was comprised of just over 4,000 stillbirths and live births each. We had 26 available variables, and they could be generally categorized as being chronic conditions of the mother, such as diabetes, asthma, conditions of the current pregnancy, so whether there was hypertension, preeclampsia, a UTI during the pregnancy, and then demographic information around the mother, so ethnicity, socioeconomic status, and age. I think the important thing to note here, these are all variables that, this is all data that we can gather without any intrusive testing. This is all routinely gathered data in a pregnancy or even before a pregnancy. So we built our models. So here are some of the key metrics that kind of indicate their model quality. So on the top, we have our receiver operated curve, characteristic curve. And what you may be able to see, depending on the size of your screen, is that's actually not one kind of blurry line. That's 4 overlapping lines, indicating that straight off the bat, our model's performance was quite similar across all models. So if I look at some of the key metrics, being here, I've chosen sensitivity, specificity, and wow, I kind of managed to say that right for once, and positive predictive value. Our sensitivity is not too bad. We're detecting about 65% of stillbirths in our training set. Our specificity is just over 97%. But the number that you're probably drawn to, and rightfully so, is our positive predictive value. And what that's saying to us is if we were to say 100 women, those are the pregnancies that are going, 100 pregnancies, those are the ones that are going to result in stillbirths. We only actually get it right about 5% of the time. And yep, that's a problem when we think of model quality. But we do have to, I guess, make it a slightly less scientific question, more almost like an ethical one in some senses. And this is, I guess, a discussion point as well, is when your goal is to produce a model that can ultimately detect stillbirths and hopefully intervene in a non-invasive way, if you can pick up 60% of them at the risk of over-diagnosing, and maybe if the intervention is only to provide mothers with more information about why they're at risk, then are we causing that much harm overall? So I guess there's no exact answer to that per se, but it is something to consider when you think of, I guess, were we successful or not? Cool. So I'll now move on to, I guess, why we're here, which is the structured fusion penalty. So in this graph here, I plotted the parameter estimates for our 4 models for all of our predictors that had 3 or more levels. So those were interpregnancy interval, mother's age, ethnicity, socioeconomic status, and presentation. And just for the sake of discussion, I'm going to focus on interpregnancy interval. And that's the length of time between the end of the previous pregnancy and the beginning of the pregnancy of interest. So with the reference being mothers who have had no previous pregnancy. So if we look in our unpenalized model and we go to make an interpretation about the effect of interpregnancy interval, we can see that mothers who wait less than 6 months between pregnancies have an increased risk factor. Then, across varying degrees, we have a decreased risk factor for anyone who waits waits more than 6 months compared to mothers, first-time mums. So you can see though that those different values, so it's effectively 5 different interpretations that you're making, even though I guess you can classify it as being a decreased risk. So we go across to our LASSO model on the right. We can see what I mentioned earlier, that being the LASSO is just selecting based on the indicator value alone. So in this instance, only waiting 12 to 17 months was the only indicator variable as a part of the predictor that was determined to be influential. And I guess then some of your questions might evolve then, what kind of interpretations can we make about interpregnancy as a whole when we kind of compare it to other variables? Is that to say that just because we're selecting a certain indicator, how can we, I guess, relate it? And it sounds confusing because I think it is a bit confusing, and that's why it's not a great penalty for this application, or any application that involves almost entirely categorical predictors. The group LASSO allows for a little bit more, an improved set of interpretations. So in this circumstance, interpregnancy interval, all indicator variable parameter estimates were shrunk to 0. Selection occurred for variables such as ethnicity and presentation, so we can kind of make interpretations about how they compare at the predictor level. What we're really interested though is the bottom right corner, and those are those structured fusion penalties. So let's have a look at the interpregnancy interval again. Here we have less than 6 months being shrunk to 0, while selection occurring across all the other levels, but also fusion. So the parameter estimate was of the same here. I think it's close to negative 0.1. So interpretation effectively becomes between 2 groupings. Our reference and women that wait less than 6 months. So if we compare to them, as long as you were to wait more than 6 months between pregnancies, you're going to have a decreased risk of stillbirth compared to that other group. And I guess there's some appreciation about that's a little bit more elegant than what we had before, where we had these kind of choppy interpretations where we had to make them at an indicator level rather than a predictor as a whole. So I guess the final thing I'll show you today will be the trace of the lambda for cross-validation. So in the previous slide, what we saw was the final estimate chosen through cross-validation. Here, I like to think about lambda as, I guess, being the pressure applied that's required to fuse levels together. So it gives a better understanding of how the levels within a predictor are related. So if we look at the variable mother's age here, though it actually ends up being estimated to 0 or just removed from the model, we can see that this line marked 1, the lambda value there, that's the very first fusion point that occurs. So interpretation from that can be that women between 30 and 34 years and 35 and 39 years effectively become one category or is closely related the most between all those levels. And you can go on and on and on, depending, I guess, on the number of levels and the fusion points you have. So I'm going to wrap that up for now. And I guess the main takeaway that I'm hoping you have from this presentation is that structured fusion penalties offer a tool to make categorical predictors more interpretable. So yes, I've applied it to stillbirth prediction here, but reality is it's applicable to any kind of circumstance where you're trying to build a model involving lots of categorical predictors, and you want to be able to make some meaningful interpretations that drive action out of that. So thank you very much. It's actually been great pulling this presentation together because it's been quite a while since I looked at this work. So it's a bit like, I guess, putting your favorite toy in a cupboard and then taking it out 6 months later and kind of refamiliarizing yourself from a little bit more of a distance. And it's been really valuable for me. So I hope you enjoyed this. And of course, please feel free to ask whatever questions. And I'm also happy to take questions by email if that's your preferred point.